Okay, in this video, we're going to talk about isomorphisms. This is section 5.6 in the book. Okay, isomorphisms. Okay, let U and V be vector spaces over the real numbers R. R could be replaced by the complex numbers. Okay, a linear map, T mapping U into V, is an isomorphism if it is one-to-one and onto. Okay, so the map has to be a linear map, and it has to be one-to-one and onto, so a bijection. Okay, so a linear bijection is another thing we might say in place of isomorphism, but this is the common language that we use. Two vector spaces for which an isomorphism exists between them are called isomorphic or isomorphic vector spaces. Okay, the idea of isomorphism exists throughout abstract algebra. You can have isomorphic groups and fields and rings and things like this. This says in essence that two vectors are essentially the same, okay, except for maybe some symbolic differences. All right, let's take a quick example. I've got a mapping T from R squared into R squared defined by the following. T of xy is 2x plus y and x plus y, and I claim this is an isomorphism. Okay, to be an isomorphism, it must satisfy the conditions of an isomorphism. The first thing it needs to satisfy is that it is a linear map. You can see that we can actually write this map in the following way. It's the 2 by 2 matrix 2, 1, 1, 1 times the column vector xy. That's the same as T acting on xy. And you remember that would automatically make that what? A linear mapping. Every linear mapping is essentially a matrix product, right? On the vector. Okay, so T is linear. Now, let's show that it is actually an onto map. Okay. Now, do you remember this? Since T maps R squared into R squared from a previous section here, okay, T is one-to-one and onto if and only if the matrix associated with this, the square matrix, is invertible. Okay, now the matrix associated with this particular linear mapping from R2 into R2 is actually what? The matrix 2, 1, 1, 1. That's going to be invertible if and only if its determinant is non-zero, right? Well, its determinant is actually 1, as you can see. So that's not 0, obviously. So T must be what? 1-to-1 and onto. In other words, altogether, it would be an isomorphic or isomorphism. Okay, let's come up with a quick theorem here. Suppose that U and V are vector spaces over the real numbers with the same finite dimension. You know, there are infinite dimension vector spaces, but we're not concerned with those. Then U and V are isomorphic. So all we actually need is what? For the vector spaces to be over the same field. Again, this could be replaced by C later. But if they have the same, they're over the same field and they have the same dimension, then they're actually going to be isomorphic. Okay, let's go ahead and get an idea why that's true. Well, U and V are vector spaces of dimension n, let's say. Okay, so let's say the dimension is n, some finite number. Then let's say these, U1 through UN and V1 through Vn, are bases for U and V respectively. Okay, so this is a basis for U, and these guys over here are bases for V. Okay, I'm going to define the following linear map, T. Okay, from U into V by the following. T of U bar I is V bar I, okay, for I goes from 1 to n. So in other words, my map is going to map the first guy over here to the first guy over there, and the bases, this guy over here into this guy over there, and so forth, all the way down to the end. This guy will get mapped onto this guy, okay? Alrighty, does that make sense? Now I'm going to make it a linear map, so I'm going to force this to what? Obey the laws of linear transformations or linear operators, right? Okay. Now let's go ahead. T is going to be 1-to-1. Let's show that it's 1-to-1 and onto. Okay, the first thing we'll show is that it's 1-to-1. Okay, suppose x bar and y bar are elements of the U vector space, and that they have the same image under t. Okay, so t of x bar is the same as t of y bar. Since t is linear, then t of the difference of u and v is going to be the same as what? T of x bar minus t of y bar. Okay, but that's going to be 0 since these guys are what? These guys are equal, right? So that's going to be 0 bar, the 0 vector in the vector space V, though. Okay, so 0 bar, the 0 vector, is different possibly in the U vector space than it is from the V vector space. Okay, so, but this is going to be the 0 vector of the V vector space. Okay, so anyways, we have this relation then. Now, x minus y. Remember, those are both elements of the vector space U up here, so their difference is also in the vector space U. So that means what? X minus y can be expressed as a unique linear combination of those basis elements, U1 through UN, right? Okay, so let's say we've done that. Okay, then if I go t of the difference, that would be t of what? The summation I goes from 1 to n, a sub I, u sub I bar. Okay? All right, but since this is a linear operator, I can move that t inside the summation sign, right? Okay, and then those are scalar multiples, so I can actually move what? T inside those scalar multiples. So I have the summation I goes from 1 to n, a sub I times t of u sub I. Okay, but what's t of u sub I? That's v sub I, right? Okay, or v sub I bar if you wish. So this is the summation I goes from 1 to n, a sub I, v sub I bar. But remember, that's supposed to be what? The 0 vector up here. So that's supposed to be the 0 vector for the v vector space. But wait, the v sub i's make what? They're a basis for the vector space v. And the only way you can get the 0 vector out of those is what? These all have to be 0. All the a's there, all those scalars, have to be 0, right? All right, that's what I've stated here. All right, but where those a's come from originally? Oh, wait, yeah, those a's were actually what? The scalars on the u sub i's representing x minus y, or x bar minus y bar. Okay, but if all those are 0, this means what? X bar minus y bar is the 0 vector in the vector space U. So in other words, x and y have to be equal. So you can see that we have one-to-oneness. So we're saying ultimately what? If I've got the images equal here, t of x bar equals t of y bar, this ultimately implies that what? X and y bar have to be equal. Okay, that makes it what? 1-to-1. Okay, how about the onto-ness? We need it to be onto also. Suppose that v is an arbitrary vector in the vector space v here. So I've got v bar as an arbitrary vector in here. Okay, it's going to have some unique expression as what? As a linear combination of vectors from the basis for v. Okay, and I've drawn that there. I've written that there. Okay, so for some scalars, a1 through an. Okay. Consider the following vector u. Okay, u is obtained just by taking all these a's and what? Sticking them onto what? The u's instead of the v's. Okay, just consider that vector for a second. U bar is defined this way. Okay, then what would t of u bar be? T of u bar would be t of the summation, right? Okay, but since t is a linear operator, I can bring t on the inside, okay, and factor out the scalars also. But what is 2t of u sub I bar? Oh, that's v sub I bar. Oh, so the summation of I goes from 1 to n of a sub I, v sub I, that's what the value is. But what was that originally? Oh, yeah, that's v, actually. So do you see, regardless of what arbitrary v you choose in the vector space v, I can always find a vector in the space u which maps onto it. Okay, so it's what? Onto also. That means what? T is a one-to-one onto mapping, so that means that what? U and V are isomorphic. Okay, so that's all you need. That's pretty easy for two spaces to be isomorphic then, right? Essentially the same space. All right, let's come down here. Let's take this example here. Show that R2, or R squared if you like that better, R2 and V, which is the span of 1, 0, negative 1, 1, 1, 1, are isomorphic. Okay? Now, I'm not going to be able to do what I did on that previous example. Remember this first example I did up here when I went from R squared into R squared? Then I just had, what, a 2 by 2 matrix, and I found its determinant, right? This time, you notice I'm not mapping from R squared into, or say R to the M into R to the N this time. I'm not doing that. So I can't access that theorem that I used in a previous video here. Okay, I can't access that theorem because my mapping isn't like that. Okay, my first vector space is R squared or R2, but my second vector space, this isn't R3, it's not R2 either, it's not R anything, you know, it's just not, all right? It's just the span of these 2, 3 vectors, okay? All right, so this is, V is actually a subspace of R cubed though, okay? But anyways, we want to show that these are isomorphic. This is going to be very easy. Okay, 0, 1, 1, 0, okay? What's its rank? Well, how many non-zero rows does this have? It has 2. So V must have dimension 2 also, right? Since this is the same as the rank, okay? Thus, R2 and V are isomorphic because they both have dimension 2 over the reals, okay? So pretty easy, all right? Let's talk about the matrix of an isomorphism. Suppose that T is a linear map here from R2 into V, and suppose it's given in the following way. T of the vector 2, 1 is 1, 0, negative 1. T of 1, 1 is 1, 1, 1, okay? Where V is the span of these two vectors here, okay? All right. Then T is an isomorphism. Why? Okay. Well, I hope you know now why from our previous theorem here. Okay. Since T is a linear transformation, okay, I'm claiming that it's supposed to be a linear transformation. Okay, I guess I should have said that. Is a linear transformation given by, okay. There exists a matrix such that what? Remember how linear transformations are always equivalent to what? A matrix product in essence, okay? All right. Let's see, 2, 1 gets mapped onto 1, 0, negative 1. So I'm looking for a matrix such that what? A times 2, 1 gives me my 1, 0, 1. Likewise, what? 1, 1 got mapped onto 1, 1, 1. So A times 1, 1 should be 1, 1, 1. Okay, I can put these together and make a matrix equation out of it. My matrix A times what? 2, 1, 1, 1, reading across, should be 1, 1, 0, 1, negative 1, 1. Okay? Read across sometimes, read down sometimes. What would the dimensions of A have to be? Okay? Well, this has what? 3 rows. Okay? This has 2 columns here. What would A have to be? It would have to be what? A 3 by 2. Okay? Have to be a 3 by 2. All right? Now, just solve this equation for A. Notice that this is my invertible matrix again. Yes, this is the same one I used in a previous example. Okay, I'm sort of combined previous examples here. Okay, that's an invertible matrix. So I could actually, what? Solve for A by multiplying on both sides by the inverse of that matrix. Okay, and I isolate A. A would be, let's read down this time, 1, 0, negative 1, 1, 1, 1, times the inverse of the matrix 2, 1, 1, 1. Okay, 2, 1, 1, 1, reading down. The inverse of that, and I multiplied through and got this matrix, 2, negative 1, negative 2, 1, 2, 3. Okay, alrighty. Now, you could go up here and test that. So here's our answer. I should box in my final answer, I suppose. You could actually come up there and test this and see if it doesn't satisfy both of these in this equation, if you'd rather write it as a matrix. But you'll see that it does work. One last point here, just a quick example. The matrix of an isomorphism need not be unique. In the previous example it was, but I'll give you an example where it is not unique. Suppose that U is the span of these two vectors, 1, 1, 0 and 1, 1, 1. And V is the span of these vectors, 1, 0, 0, negative 1, 2, 1, 0, 1. Okay? All right. Now I'm going to imagine a linear operator between the two of them. T maps 1, 0, 1 onto the first vector there, 1, 0, 0, negative 1. But T of 1, 1, 1 is 2, 1, 0, 1. Okay? So I just map this guy into this guy and this guy into this guy. And I'm going to make it a linear map here. Okay? What would the matrix of A be? Well, just like the previous example then, A would have to satisfy the following. A times what? 1, 1, 0, 1, 1, 1 would have to be the matrix 1, 0, 0, negative 1, 2, 1, 0, 1. Okay? Now, if you actually sit down to solve that, what I did was take the transpose of both sides because you're very used to using what? Elementary row operations. Okay? So I'll imagine on each side on the left, you're multiplying by what? Elementary matrices that are equivalent to row operations. Okay? So that's what you're used to here. So you imagine that happening to both sides, so that's not going to change A transpose there, and therefore ultimately not A. But anyways, add negative 1 times the first row to the second row, and I'll do it on both sides of the equation, and I get this following situation given here. And then I'll take transposes again, okay, and I have A times 1, 1, 0, 0, 1, 1 equals 1, 0, 0, 1, 1, 1, 0, 2, okay? So a slight change, okay? Notice the dimensions of A that would have to be 4 by 3. Okay, this is going to give us considerable latitude here. Okay, let me give you an example. A could be this vector. Let me just show the non-uniqueness here. Okay, remember you're just trying to satisfy this equation up here. Okay, that one. You will see the following both hold. Okay, A could be this vector, for example, 1, 0, 0, negative 1. Zeros in the second column, and then 1, 1, 0, 2. It will satisfy that equation right there, which will also satisfy this original equation up here. Okay? But it'll satisfy it. No problem. Okay? All right? This one will also work. In fact, there's infinitely many ones that will also work here. Okay? You just got to make the sum. Let me show ultimately what's happening when we multiply on this. Okay? You're just going to make sure when this multiplies here that the sum of these two columns adds up to the first column over here. And then what? The last column is equivalent to the column there. Okay? That's all I'm doing. Notice that the sum of these two columns is indeed that column right there. Okay? Sum of these two columns still gives you 1, 0, 0, negative 1, just like I want. Okay? So there are cases where the matrix would not be unique. I don't think your book made that point very well. Anyway, so there you go. I hope you understood that.